Welcome to this online training about the hardened network-on-chip interconnect found in Altera Agilex FPGAs. My name is Steve. This training is available for desktop viewing, as well as in a format compatible with portable devices, both available from the same link included in your registration email. For either version, while watching the training, use the controls at the bottom and side of the screen to navigate to any point. Feel free to pause the training at any time to experiment with the software. When you are done with the training, please use the link provided in the registration email you were sent to provide us feedback on the training and ways in which it can be improved. I'll remind you about that later. This is part 2 of a 2-part training that provides a general overview of all aspects of working with the network-on-chip, or NoC hardware, found in certain Altera Agilex FPGAs. The listed objectives cover the main aspects of the NoC discussed in the training. In Part 1, you learned about the basic architecture of the NoC and how it works, looking at the advantages of using the NoC with an external memory interface, or EMIF, or with the high bandwidth memory, or HBM, found in these devices. Here in Part 2, you'll learn how to implement a NoC design in the Altera Quartus Prime software using IP and other available tools. You'll learn about the device resources required to implement a NoC design and how to plan your design to make best use of those resources. Finally, you'll learn some techniques for optimizing different aspects of a NoC design, including performance and resource use. If you missed Part 1, you can find the registration link for Part 1 here and near the end of this training. For this e-learning, it is recommended that you have experience using the Altera Quartus Prime software and are comfortable creating, parameterizing, and instantiating IP in a design. You should also be familiar with creating project assignments using the assignment editor or pin planner. Experience with Interface Planner is also helpful. You can find training on all these topics at the Altera FPGA Training homepage or on the FPGA Training Developer page, both linked here. While not necessarily required to build a NoC design, experience with Platform Designer will be helpful if you decide to use the Platform Designer design flow. Platform Designer is required if you'll be implementing a design that includes the Hard Processor System, or HPS. The e-learnings linked here about Platform Designer will help you get started with this tool. Finally, as mentioned, the NoC is used for high-performance data transfers with external memory, such as DDR4 or DDR5, or on-package HBM, so knowledge of the memory you'll be connecting to will be helpful as well. See the additional e-learning links for details. Now with the architecture of the NoC in mind, let's look at how to implement a NoC design using the Altera Quartus Prime Pro Edition software. To integrate the NoC with a design, it is important to follow a specific design flow. There are many things to take into account to get the best performance out of the NoC, and following the prescribed design flow is the best way to do this. First, you'll need to decide whether you want to use Platform Designer exclusively to build your design, or build your design through IP instantiations and a new tool called the NoC Assignment Editor to make the connections through the NoC. The NoC Assignment Editor can be used with both of these flows, but its use for making connections is optional if you build and connect everything in Platform Designer. Note that Platform Designer is required if your design includes a NEOS 5 processor or the HPS. Next, create and parameterize the memory IP to be used with the NoC. Both the EMIF and HBM2E IP include parameter options for how they will work with the NoC. The EMIF IP also has an option for bypassing the NoC. Configure and generate these IP as appropriate. With the memory IP created, you can create and configure one or more instances of the NoC initiator IP for configuring the INIUs that will connect to the memory interfaces via the NoC and TNIUs. This IP is also where you decide whether to use the fabric NoC for a particular INIU. If the HPS is to be used with a dedicated memory interface, note that this is done through the HPS and HPS EMIF IP configurations, so no separate initiator IP is required. Next, create the NoC clock control IP to specify the reference clock for the NoC. 2 instances of this IP are needed if both the top and bottom NoC are to be used. With the NoC IP created, specify connections between the INIUs and the TNIUs that will access the memory IP. This can be done either directly in Platform Designer or using the NoC assignment editor after performing analysis and elaboration. After making the connections, perform analysis and elaboration. For the NoC assignment editor connection flow, this will be the second time this compiler process is performed, but it is required for specifying options for the connections established in the previous step and to create a file required for simulating the NoC design. Now, for both flows, use the NoC assignment editor to group the NoC and target IP with either the top or bottom NoC of the device. You can also specify options and performance optimization goals for the connections established through the NoC. You can now simulate the design if desired. Before fully compiling the design, specify the physical placement of the INIUs and TNIUs. Use Interface Planner to select the most optimal and legal locations for these ports. Finally, compile the design, verifying the placement and performance of the NoC using reports generated by the tool. The easiest way to get started with the NoC is to generate a complete example design project. Both the EMIF and HBM2E IP parameter editors can generate a complete project that includes the memory IP connected through the NoC to traffic generator logic in the FPGA fabric. The configuration and connections for the clock control IP, INIUs, and TNIUs are all included. The logical assignments created by the NoC assignment editor are set as well, including grouping to the top or bottom NoC, making connections between INIUs and the correct TNIUs, and setting the appropriate addresses for the host logic in the fabric to access the memory IP through the NoC. All these assignments will be discussed later. The example design also includes simulation models and test benches to simplify the process of simulating the design. If you are using the board-aware flow with a development kit or a custom board, either directly in the Altera Quartus Prime software or in Platform Designer, the example design can be programmed to your board immediately after compilation. See the Altera Quartus Prime software user guide or the Platform Designer user guide linked at the end of this training for details. To create an example design, configure the appropriate memory IP as needed and choose options for the example design itself on the Example Design tab as shown here for both EMIF and HBM2E. The user guides and training provide detail on the options available. When you have finished configuring the IP, click Generate Example Design. A complete Altera Quartus Prime software project is generated in the location specified. Open the Example Design Projects.qpf file to examine and compile the design. Whether you use an example design or not, you must configure the target memory IP appropriately to use the NoC. Here are the parameter settings in the EMIF IP specific to doing this. First, you must set the Use NoC parameter to true. This is set to true by default, but can be set to false to bypass the NoC for EMIF access. On the Example Design tab, if creating an example design, set the core clock frequency parameter to set the frequency of the clock that will drive the traffic generator and the INIU on the fabric side of the NoC. Set the NoC ref clock frequency parameter to match the clock speed set in the NoC clock control IP, discussed later. The NoC-related settings for HBM2E as the target memory IP are highlighted here. You can enable up to 8 channels for accessing the HBM2E. Each channel is 128 bits wide, but divided up into 2 64-bit pseudo channels. When channels are enabled on the General tab of the parameter editor, extra tabs appear for each channel as shown. On each channel tab, turn on the option to enable the pseudo BL8 mode. This sets the burst length of the channel to 8 instead of the default of 4, allowing for data accesses through the full channel to be 64 bytes using 2 sequential BL4 transfers, instead of only 32 bytes with a single BL4 transfer. This makes the most efficient use of data access through the NoC. The Example Design tab includes a number of NoC configuration options. First, specify the reference clock frequency for the NoC to match what is set in the clock control IP, discussed later. Then, choose how traffic generators for each channel will access the HBM. By default, each traffic generator accesses a particular pseudo channel connected through a single dedicated INIU. However, if all 8 channels are enabled, a 16 to 16 crossbar can be implemented in the FPGA fabric to allow any traffic generator to access any pseudo channel connected through any INIU. This provides more flexibility, but there is more of a possibility of contention between multiple traffic generators trying to access the same channel or pseudo channel. Next, choose an option to enable or disable the use of the fabric NoC. Recall that this sets the read data channel to 512 bits wide and enables the use of M20K on-chip memory blocks in the fabric for temporary read data storage. The options available enable this fabric NoC with the additional option to set the write data channel to 512 bits wide as well. You can also choose whether to share clocks between the read and write channels or use separate clocks to improve either read or write speeds, depending on the application. The NoC bridge hardware frequency option sets the clock used to drive the other 256-bit wide channels when the 512-bit wide option for both the read and write channels is selected to enable the fabric NoC. This option switches to read-only AXI data path frequency if the 512-bit wide path is enabled only for the read channel to specify its separate clock frequency from the other channels. The AXI4 Lite support option lets you enable a separate dedicated INIU for AXI4 Lite transactions to the HBM, or use a shared INIU for both AXI4 and AXI4 Lite transactions. As mentioned earlier, AXI4 Lite is used for control and status register access. Note that shared AXI4 Lite access prevents the use of the fabric NoC. Finally, the NoC read and write bandwidth and transaction size options indicate the anticipated bandwidth and transaction sizes based on the other settings specified in the parameter editor, and assuming the most optimal placement of the INIUs and TNIUs in the device. These values can be set for each INIU to TNIU connection using the NoC assignment editor, discussed later. If you are not creating an example design, you'll need to create one or more instances of the NoC initiator Altera FPGA IP to connect FPGA AXI4 manager interfaces to the fabric side of the NoC. A single instance of the IP can be configured to implement multiple identical INIUs, so multiple instances are only needed for each unique INIU configuration, or if both the top and bottom NoC will be used. Specify the number of AXI4 and/or AXI4 Lite INIUs to implement with this instance of the IP, and whether they should share a common clock and reset, or if they should all be independently controlled. Set the AXI4 data mode option to a value greater than or equal to 512 bits to enable the fabric NoC for the INIUs defined in this instance of the IP. You can also set data modes of 288 and 576 bits and use the AXI4 user sideband signals, R-user and W-user, for transmitting additional data. Optionally choose to use separate clocks for the wider data channels to run them at higher speeds for better bandwidth and performance. Also choose how the AXI4 handshaking mechanism should be implemented, either with pipeline registers for improved performance or without the registers to reduce resource usage. Using the pipeline registers can help meet timing on the valid and ready signals used for all AXI4 channels. Finally, the NoC bridge configuration options let you configure how quality of service for read and write transfers will be implemented. As mentioned earlier, QoS can be controlled using the standard AX-QoS signals that are part of the Axie4 standard, or it can be set to fixed priority values controlled by hardware in the INIU. The NoC priority settings specify the fixed values to use for reads and writes, with 0 being lowest priority and HPS in your being highest, with a dedicated EMIF. Enable use of the NoC in the HPS IP parameter editor as shown. It's not necessary to add the initiator IP in this situation, unless you have other fabric managers who will access a separate EMIF clock control IPM and set the reference clock frequency. Also select whether the memory interface for the HPS will be single or this IP is required for single channel PLL that clocks the INIU connection and the SSM the MPFE to configure the NoC and should be used for interfaces light access to target IP. If the EMIF will be greater than the speed of the reference clock to use, or you want to use interleaving, if you will be using both the top and bottom NoC, add two instances of this IP. Uses both INIUs. The designation of whether the IP is used for the top or bottom NoC larger memories will be set later and permit interleaving between the two EMIF channels. The next step is to make connections between the HPS dedicated EMIF. First, the IO96 bank with closest to the HPS must be used. Shown here is the Platform Designer system for an example design created from the EMIF IP parameter editor. At the top, you can see the EMIF IP with two Axie4 subordinate interfaces named T0 Axie LNoC for the Axie4 Lite interface and T0 Axie4 NoC for the standard Axie4 interface. The T0 naming indicates that these interfaces will connect to TNIUs on the I/O periphery side of the NoC. These interfaces connect through the NoC using the connections highlighted in blue. Two instances of the NoC initiator IP are used, one for the Axie4 interface and one for the Axie4 Lite interface. The instance naming, NoC init versus NoC init Lite, indicates which is which. While these could be combined together into a single instance of the IP, the generated example design always separates them into two separate instances. On the initiator IP, you can see Axie4 manager interfaces named I0 Axie4 NoC, with I0 indicating these are the INIUs. The example design automatically connects the correct manager to the correct subordinate. If the initiators were combined into a single IP instance, two manager interfaces would be available and appropriately named. Base addresses are set for the Axie4 and Axie4 Lite subordinate interfaces of the EMIF IP to indicate the starting addresses at which the INIUs will access the target IP through the NoC. Below the EMIF IP is an Axie4 Lite driver IP for CSR access to the EMIF and the test engine IP. These components get implemented in the fabric and connect to the INIUs with the connections highlighted in purple. These Fabric Manager components interfaces are getting routed through the NoC via the INIUs. Base addresses set on the subordinate interfaces of the INIUs indicate the starting address at which the Fabric Managers will access the INIUs. Finally, in the middle are the System PLL, named User PLL, and the NoC Clock Control IP. The System PLL clocks all the fabric side components, including the INIUs in this design. You'll notice that the NoC Clock Control IP does not connect to anything in the system other than its external reference clock. The NoC PLL is already connected to the NoC in hardware, and the NoC assignment editor will be used to specify whether it drives the top or bottom NoC. For the Platform Designer flow, generating the complete system stores the connections made in the tool in the generated.qip file, which gets passed to the Altera Quartus Prime software for subsequent analysis and elaboration. Recall that for the NoC assignment editor connection flow, you can use either Platform Designer to build the design or standard RTL instantiations. If you choose to use Platform Designer with this flow, add components to the system as shown on the previous slide, but leave the Axie4 NoC interfaces unconnected and generate the system. These were the blue connections on the previous slide. You may want to do this if you still want to use Platform Designer to build your larger system design, but want to manage all the NoC connections separately without having to edit your Platform Designer system. If you're using RTL code to instantiate the NoC IP, these interfaces are not available for connection at all, since the connections must be made in the NoC assignment editor. Simply instantiate the initiator and target IP. For either option, perform analysis and elaboration. This builds the design hierarchy and establishes the INIUs and TNIUs that will be connected in the NoC assignment editor, accessible from the assignments menu. You'll then create group and connection assignments in this tool, described next. For both the Platform Designer flow and the NoC assignment editor connection flow, you'll use the NoC assignment editor to create logical assignments for the NoC, though some of these assignments will already be created if you use the Platform Designer flow. The tool is organized into 3 tabs. On the first tab, named Group, specify group names for all the NoC elements listed. You can use any names you wish. All elements with the same group name will be grouped to either the top or bottom NoC, so only a maximum of 2 groups can be specified. Group assignments are stored in the .qsf file, just like any other assignments created in other tools, such as the Pin Planner or Assignment Editor. In the example shown here, created by an example design, only one HNoC will be used, so all elements are grouped into NoC Group 0. The selection of which HNoC each element is associated with is not set here. When physical assignments are created later, elements of each group will be physically placed at the top or bottom NoC. Next is the Connection tab. Sub-tabs with the group specified on the Group tab appear here for making connections for both HNoCs. If you did not specify group names on the Group tab for either flow, the sub-tab here will appear as ungrouped. You must specify 1 or 2 groups on the Group tab before making connections. On the left is a list of all INIUs, and each column on the right represents a TNIU. Use the checkboxes to make the desired connections between INIUs and TNIUs. If you used the Platform Designer flow to make connections, connections will already be enabled here and grayed out, so they cannot be edited without going back to Platform Designer. If for some reason you make connections here in the NoC assignment editor and then go back to Platform Designer and make the same connections, the connection cell in the NoC assignment editor will be highlighted in yellow, indicating a conflict of assignments between the 2 tools. The last assignment made will take precedence, but delete the connection in either Platform Designer or in the NoC assignment editor to resolve the conflict. Finally, the Attributes tab allows you to specify important attributes for each connection made on the Connection tab. Again, you must create a group or groups on the Group tab and make connections on the Connection tab in order to specify attributes for a particular connection. Each row represents an INIU to TNIU connection from the Connection tab. First, set the base address for the INIU to access the connected TNIU through the NoC. If you used the Platform Designer flow, this will already be filled in with the address set in Platform Designer and grayed out so it cannot be edited here. Much like Platform Designer, there is an Auto-Correct Base Address button to quickly set non-overlapping address spans for INIUs that connect to multiple TNIUs. The remaining attributes set the desired read and write bandwidth for each connection and the read and write transaction sizes to use. The bandwidth values specified here should be based on the expected traffic for the connection, taking into account the INIU data width, the INIU clock speed, and any possible TNIU limitations. The default values of 0 indicate you are not imposing any limits on the bandwidth. Note that it may be necessary to intentionally limit the bandwidth to avoid oversaturating the NoC. The NoC performance report, discussed later, will estimate whether these values are achievable based on the final physical placement of these NoC elements. The transaction size can be set to a power of 2 number of bytes from 32 up to 4096. Since a transaction through the NoC is broken down into 64-byte packets, it's recommended in most cases to set these options to 64 bytes or greater. When you are finished creating the logical assignments, validate and save them to the .qsf. Validation checks to make sure there is one PLL per group, that every INIU is connected to at least one TNIU, and that there are no overlapping address spaces for INIUs connected to multiple TNIUs. When you are done with the NoC assignment editor, synthesize the design to be able to simulate it and prepare for physical placement of the NoC elements. A NoC-based design can be functionally simulated just like any other design with IP models and a test bench generated by the Altera Quartus Prime software. However, in order to model the INIU to TNIU connections through the NoC, special registration function calls by the simulation are required, since these connections are only defined in project assignments, not the design netlist. These function calls are defined in an include file that gets saved in the project directory or with the generated simulation models for the design. To create the file, for the platform designer flow, simply generate the system. For the NoC assignment editor connection flow, be sure to rerun analysis and elaboration after validating and saving the logical assignments created in the NoC assignment editor. The file has an extension of .inc. To use the file in the simulation, include it in the test bench file with tick include. Then, create a macro in the test bench named sim_top_path that defines the location in the design hierarchy where the INIUs and TNIUs are located. For details and an example setting up the test bench, see the NoC user guide. With the logical assignments in place and the design synthesized, physical assignments must be created to choose locations for the target IP and the INIUs and TNIUs. The choices made for physical assignments directly affect the performance of the target IP via the NoC, so it's important to carefully follow all optimization guidelines discussed in the NoC user guide, some of which will be discussed here. The easiest way to make these assignments is to use Interface Planner. This is not required, but just compiling the design and letting the fitter select the physical placement of the NoC elements will not be optimal. For more information on using Interface Planner in general, and more specifically for a NoC design, see the NoC user guide as well as the documentation and training links found at the end of this training. When you use Interface Planner with a NoC design, the target IP appears as usual in the design element list on the left, along with the INIUs, TNIUs, and other elements that require physical location assignments, depending on the design. To start, select legal locations for target IP, including HPS-specific EMIF, standard EMIF, and the HBM. The user guide explains what element of these target IPs should be placed first. Click the arrows next to the appropriate element, or right-click to select the option shown to generate the list of legal locations for the selected element. Selecting one of the legal locations in the list on the right highlights that location in the graphical view in the middle to give you an idea of where the element will be placed. Choose to place the selected element at one of the legal locations by double-clicking or right-clicking the desired location. After placing the initial element, repeatedly click the Auto Place Fixed button to place all other elements that have only a single legal location now based on the location selected for the target IP and the groupings selected in the NoC assignment editor. In the example shown here, the RZQ pin of the EMIF is the recommended first element to place. A number of legal locations at both the top and bottom of the device are available, since this is the first IP placed. Since the EMIF was grouped with other NoC design elements, placing the EMIF at the top or bottom edge of the device establishes that the other grouped elements must be placed at the selected edge as well. The Auto Place Fixed button guarantees that this grouping is enforced, and subsequent legal location lists for NoC design elements that have multiple legal locations will be restricted to the edge selected for the EMIF. Once the target IP is placed, switch to the Interface Planner NoC view. This view highlights the I/O periphery as well as the INIUs and TNIUs. Zooming into the NoC, you can see the representation of the INIU and TNIU locations, similar to the diagrams shown earlier. The NoC switches do not appear in the Interface Planner, but they've been added here to better illustrate the elements that make up the NoC and how they are connected. Continuing the example from the previous slide, on the target side of the NoC, the pink TNIU is the auto-placed Axi4 light target for the EMIF. Recall that the Axi4 light target is accessed through the PLL SSM NoC segment. The NoC network for Axi4 light is not shown here. The white TNIUs are legal locations for the target connection to the EMIF. The EMIF target interface is placed on a TNIU just like any other design element. INIUs on the fabric side of the NoC can be placed as well. When an INIU and its connected TNIU are placed, a blue path appears indicating the connection path through the NoC. As mentioned, the optimal placement is to have the INIU and TNIU vertically aligned with each other as shown on the left. Of course, this may not always be possible. If the INIU and TNIU are not vertically aligned, the blue path shows the connection through the NoC switches and the horizontal data movement that will be required. The placement on the right illustrates this. Data will need to go through 3 switches instead of only 1. Interface Planner makes it very easy to make these physical placement assignments and see how they will affect the design. When you are done placing all elements, validate the placement plan, export the placement constraints, and incorporate them into the Altera Quartus Prime software project. See the links at the end of the training for information on completing the use of Interface Planner for placing design elements. As you are placing design elements in Interface Planner, you can generate a NoC performance report at any time. Simply double-click the task shown. The report lists all INIU to TNIU connections, the requested bandwidth numbers specified in the NoC assignment editor, and the physical placement of the initiator and target you've selected. If a row in the report appears red, it indicates that that connection with the current placement cannot meet the requested bandwidth requirements. The message column will provide more detail as to why there is an issue, for example, an oversaturation of the INIU or the NoC bandwidth, perhaps due to other connections using up the available horizontal links. Use the information provided to adjust the placement and verify bandwidth requirements are met. At this point, the design is ready for compilation. Perform a full compilation to place and route the NoC design elements and any logic in the fabric. 2 NoC-specific reports are available in the compilation report after a full compilation. The NoC connectivity report, found in the plan stage folder of the FITR report, verifies that the connections and addresses specified in either Platform Designer or the NoC assignment editor were implemented. The NoC performance report, also found in the plan stage folder, is similar to the performance report available in Interface Planner. However, this report uses actual clock frequencies to verify the NoC is meeting the performance requirements as opposed to the estimated frequencies used by Interface Planner. Like the Interface Planner performance report, the final performance report for the NoC will highlight connections in red that will not be able to meet the requested bandwidth requirements. It also includes the reasons why the connection cannot achieve the desired bandwidth. Here is a list of the common causes of congestion reported in the tool. If the values specified in the NoC assignment editor exceed the physical limits of what is achievable for an initiator or a target, the connection will not be able to meet that requirement. Other causes of congestion include exceeding the bandwidth capability of the switches and horizontal links through the NoC, slower connections sharing resources with faster connections, and too many active horizontal link connections in the same direction, requiring arbitration and delays in data transfer. The solution to many of these issues may be INIU or TNIU placement, but adjustments to the placement of target IP may be required as well. See the user guide for an example of a performance report indicating a congestion issue. Besides the compilation report, you can use the chip planner to verify the placement of NoC design elements. In the chip planner tasks window, run a resources report and select a NoC resource from the list as shown. When the report is run, the NoC resources are highlighted in color in the chip view. The chip planner shown here is from the EMIF design example shown earlier, with the view zoomed in on the top IO96 bank used for the EMIF. You can see the in-use elements of the IO96 along with the INIUs and TNIU. The Axi4 Lite TNIU is not shown, but an additional report could be run to add it to the view. To finish up this training, let's look at a few recommendations for planning out the use of resources for a NoC design and strategies for optimizing a design. Resource planning is essential for creating a high-performance NoC design. Typically, resources are planned and assigned late in the design flow. However, this must be performed earlier when planning on using the NoC. The resources to think about are listed here. Planning the usage of general-purpose I/O, the LVDS SerDes, and other low-speed interfaces is important because connecting signals from the fabric to I/O pins or using other resources in the periphery may block the usage of the NoC or elements of target IP. Avalon streaming is a common interface for device configuration, but its use could also block certain I/O banks and byte lanes. Of course, the I/O and internal resource usage for target IPs like EMIF, HPS EMIF, and HBM2E will govern many design factors, including board design, power, and memory bandwidth through the NoC. While the fabric NoC can greatly improve memory read bandwidth, it does increase core area utilization, including the consumption of on-chip RAM blocks. Finally, the usage of Axi4 Lite interfaces with the NoC and target IP must be planned alongside the main Axi4 interfaces of the INIUs and TNIUs. Deciding whether the Axi4 Lite interfaces use dedicated INIUs or share an INIU with an Axi4 interface can affect performance of the NoC. For all of these, see App Note 1003, linked at the end of this training, for details and other factors to consider. Looking at I/O bank blockage a little more closely, the use of certain INIUs, Avalon streaming device configuration options, and low-speed interfaces block certain byte lanes in the I/O banks. Conversely, the use of certain I/O byte lanes that bypass the NoC can block the usage of certain INIUs. To help prevent these blockages, if possible, place low-speed I/O closer to the left or right edge of the device. This leaves more central and adjacent INIUs available for EMIF and HBM2E access. Using Interface Planner to place the high-speed interfaces can help to avoid these blockages and leave room for lower speed I/O. When implementing an EMIF, one of the biggest decisions will be whether to even use the NoC or not. The NoC does introduce the most amount of latency compared to using one of the available bypass modes, but bypassing the NoC will block the usage of certain INIUs that could be used for other high-speed data transfer. However, with the NoC, you can achieve the highest possible performance and bandwidth for your application, especially when used along with the fabric NoC. As mentioned, use vertically aligned INIU to TNIU connections if possible to reduce bandwidth sharing through the HNoC. Again, App Note 1003 details all the available options and the achievable bandwidth for each. For the HBM2E, the maximum achievable bandwidth is 820 gigabytes per second. For a single HBM stack, this is 410 gigabytes per second. The only way to achieve this bandwidth is to enable the use of all 8 channels of the HBM. Recall, there are 2 pseudo channels per channel, so 16 separate INIU would be required to connect directly to all 16 pseudo channels of the stack. Once all channels are enabled, placement of the INIUs is key. There are 9 local INIUs vertically aligned with the HBM2E UIB. However, most of the TNIUs are paired and connect through a single NoC switch instead of individual switches for each TNIU. As such, to get the best performance, use the 9 local centralized INIUs and distribute the remaining 7 from the NoC segments to the left and right of the HBM2E segments. There is no way to avoid latency through extra horizontal data movement, but the bandwidth of HBM2E makes up for this. If you don't need the maximum bandwidth, consider using just the 9 centralized INIUs, which will also avoid blocking the usage of the INIUs on the adjacent segments. It's also important to note that even with 16 INIUs and usage of the fabric NoC, the memory bandwidth of the HBM2E still cannot be saturated in a -1 speed grade device. Once again, AppNote 1003 reviews what bandwidth is achievable with these devices and provides examples of recommended INIU usage and placement. Next, let's look at Axi4 Lite usage in more detail. As mentioned, this simpler version of the Axi4 standard is used for CSR access to the memory IP, including getting the status of memory calibration. An Axi4 Lite connection is required for EMIF and optional for HBM2E. The Axi4 Lite TNIUs are accessed through a separate service network. Axi4 Lite traffic from an INIU travels the length of the HNoC and through a bridge in the PLL SSM NoC segment to then access the Axi4 Lite TNIUs in each NoC segment. When configuring the INIU IP for access by Fabric Axi4 managers, you can choose to have Axi4 Lite interfaces share an INIU with an Axi4 interface, or use separate dedicated INIUs for Axi4 Lite access. The use of dedicated INIUs for Axi4 Lite may make it difficult to find enough INIUs to access for multiple EMIF or full bandwidth HBM2E designs. However, using dedicated Axi4 Lite initiators is a better option for performance, since the initiators won't need to switch back and forth between regular and sideband traffic. If possible, place Axi4 Lite INIUs closer to the PLL SSM NoC segment to minimize horizontal latency through the NoC. Planning your design's clocking scheme is essential for achieving a high-performance design. There are 4 schemes available. Use the scheme that works best with your selected device speed grade and the bandwidth you want to achieve. The first option is to not use the fabric NoC. This means both the read and write data paths will be 256 bits, and the same clock will be used for both. Use this scheme if you don't need the additional bandwidth provided by the fabric NoC and you want to minimize resource usage. Remember that the fabric NoC uses device logic and 16 M20K on-chip RAM blocks for each INIU, so this option could save a lot of resources for other purposes in the design. The remaining options all make use of the fabric NoC by increasing either just the read data path to 512 bits, or increasing both read and write data paths to 512 bits. If both read and write paths are increased to 512 bits to enable the fabric NoC, the same clock is used for both. This is the symmetrical data path option. This option is good for saturating the HBM bandwidth on slower -2 and -3 devices, but it will of course use additional fabric resources to implement the fabric NoC. If just the read data path is increased to 512 bits, you can choose an asymmetrical data path option. Use either a common clock for both reading and writing, or a separate clock for each. If the same clock is used for both read and write data paths, you can saturate the read data path, but timing closure will be more difficult because a single, faster clock will be needed for both the INIU and in the core logic. Faster clocks in the core always make it more difficult to meet timing. If a separate clock is used for the asymmetric data paths, read bandwidth can be saturated, but write bandwidth cannot due to the smaller bus width. However, it will be easier to close timing because the read clock frequency does not need to be as fast to still be able to saturate the read bandwidth. As before, for more detail on the clocking schemes, see AppNote 1003. Let's conclude with a look at recommendations for optimizing the performance of the NoC. There are many things you can do to improve the performance of a NoC design if you're not able to achieve the desired bandwidth specified in the NoC assignment editor. First, and most important, try to minimize horizontal data movement through the NoC. This means placing INIUs and their connected TNIUs as vertically aligned as possible. As shown earlier, the interface planner is helpful in visualizing and achieving this type of placement. Maximize the clock used for the INIUs and the TNIUs if you can. Check what clock speeds you can use for your selected device speed grade, and make sure you can close timing on the design at the speeds you select. Use a recommended topology for your connections through the NoC. AppNote 1003 provides many examples of recommended topologies depending on your use of certain target IP. For both EMIF and HBM2E, try adjusting the memory access traffic patterns. Certain options and patterns can increase memory bandwidth. Again, see the app note and the appropriate memory IP user guide for details. Adjust the size of AXI4 transactions to make best use of the data widths you've configured. The AX size and AX len signals of the AXI4 standard let you do this easily. For example, if you set AX size to transfer 64 bytes and AX len for a single transfer in a transaction, you can fill the standard 256-bit data path and send 64 bytes over 2 beats. If you use the 512-bit data path to enable the use of the fabric NoC, you can send the same amount of data in only 1 beat. Finally, if you can determine that a particular NoC connection is causing congestion, you can simply throttle that connection's bandwidth in the NoC assignment editor to allow other connections to take priority. The NoC user guide and AppNote 1003 have all the details on these techniques. Here are some final recommendations. When accessing an EMIF, be sure to take advantage of large data bursting to help saturate the bandwidth. If your design is read-heavy, be sure to enable the use of the fabric NoC to take advantage of its added bandwidth and speed. Remember, this also can help with congestion issues by getting data away from the NoC and periphery. If your traffic is more write-heavy, connect directly to the NoC to get the data to the target IP more quickly. For AXI4 managers in the fabric, make sure they have appropriately aligned register boundaries to avoid unaligned accesses that require additional soft logic to resolve. Finally, if you don't have enough INIUs for your design, you can still make soft connections to target IP. Doing this artificially creates additional ports. The best way to do this is to make the connections in Platform Designer, since the generated soft interconnect will automatically include arbitration logic that can switch between which soft logic gets access to a connected INIU. Again, check AppNote 1003 for details. And that concludes this training. To summarize, we looked at the network-on-chip hardware found in Altera Agilex devices and why you may want to take advantage of this unique architectural feature to greatly improve the performance of your design's memory interfaces. We stepped through the design flow for implementing a design that uses the NoC, including the use of Platform Designer, the NoC assignment editor, and interface planner. We looked at the resources needed to implement a NoC design and how to make choices in your design to make best use of those resources. Finally, we discussed some recommendations for optimizing a NoC design. There are many resources available to help you with creating and optimizing designs that use the NoC. The documentation resources listed and linked here should be the first ones you visit. The NoC User Guide and AppNote 1003 are your main resources for implementing a NoC-based design. Use the EMIF and HBM2E IP user guides for details on configuring these target IPs for your application. For basic information about the Altera Quartus Prime software, including the use of Platform Designer and Interface Planner, see the appropriate user guide, all linked here. Besides documentation, there are many e-learnings available on memory interfaces, Platform Designer, and Interface Planner. The Memory Interfaces Learning Plan includes everything you need to build an external memory interface for an Altera Agilex FPGA. The HBM2 e-learning discusses the HBM found in Altera Stratix 10 MX FPGAs, but much of the implementation is the same for Altera Agilex FPGAs. The Introduction to Platform Designer e-learning will help you get started quickly with this important tool, and the Interface Planner e-learning will walk you through all the steps to easily make physical location assignments for all high-speed I/O-related IP in your design. This concludes the training. If you missed Part 1, you can register for free at the link shown here. To learn about additional resources available to you from Altera, continue to the next slide. Altera offers many options for learning about our FPGA products and for training on their use. The Altera YouTube channel contains a number of 5-minute quick videos, along with longer, more in-depth training. The Altera training website is the place to go to learn about our recommended curriculum for every type of user and to register for a class. While there, you can register for over 300 e-learning courses made up of narrated slides presented in an interactive player, some of which include labs and demos. You can also register for one of our full-day instructor-led training classes taught by experienced training engineers, either in person at a local office or virtually over the web. All instructor-led courses have hands-on lab exercises to practice the concepts you learn. If you need further assistance, Altera provides many self-help resources. Check out the landing pages, accessed from the main Altera website, that are dedicated to specific FPGA technologies like high-speed interfaces and external memory. Finally, you can also view and post questions to the community forum, monitored by skilled Altera application engineers. One more thing. You will receive a link to a short survey where you can provide feedback. We'd greatly appreciate it if you'd fill out that survey. We're constantly updating and improving our training materials, and your feedback helps us create the materials that you want. Thank you for your feedback. My name is Steve, and I want to thank you for taking this training on the network-on-chip hardware found in Altera Agilex FPGAs.